So the topic for today is to continue looking at the Heisenberg uncertainty principle and in particular running through some examples of how to apply the principle to make order of magnitude estimates. You will recall the form of the principle simply says, and we've gone into the definitions quite clearly, that after a measurement, the residual uncertainty in the position of the particle and the momentum along the same direction cannot be reduced below a certain fundamental limit where the product of these quantities is at least the fundamental Planck's constant h bar divided by 2. In terms of the example applications we've been looking at, we noted that there are two broad types of applications. One has to do with the evolution of a particle in time or also understanding the trajectory of particles. A typical question is one that we worked through. Where is an electron, say, after 1 second of time? What is the resulting minimal uncertainty? We were then looking at the application to energies of systems. We solved and looked at the problem of a particle in a box, where we noted that just the fact that you localize a particle, there's a confinement energy, sometimes called a localization energy, associated with that confinement, because that confinement implies a certain range of delta x, which then implies that there is a minimal spread in the momentum distribution, which then results in kinetic energy. And that energy turns out to be order of magnitude. Our estimate was about h bar squared over twice the mass of the particle times the length squared into which it's been localized. Now we found a very interesting application of this. We looked at macroscopic objects, and of course, via the correspondence principle, that minimum energy is really quite low. You can place a macroscopic particle on a table somewhere very still, and it will have very, very little energy. However, if we go to a case where we have an object with a very small mass, such as an electron, and you confine it to a very small region, say within a hydrogen atom, which has a typical size that's well known is about 0.529 angstroms. If you do that, then you get an energy that actually is not insignificant, at least as far as electrons are concerned. You get an energy that's about 13.65 electron volts, and that was very intriguing because that is precisely the energy of the known lowest energy state of the hydrogen atom. So what we will then focus on today, the focus for today will then actually be to apply Heisenberg uncertainty to predict the not only the energy of the hydrogen atom, but something that we really had to depend upon outside information for. Previously, I had to tell you the size of the hydrogen atom. Now we're going to be able to predict it ourselves with a slight variant on the type of analysis we've been carrying out. So today's topic then is to use Heisenberg uncertainty principle to predict the energy and size of the hydrogen atom.